So, um, we've talked about the basics of chemicals and chemical bonds. We're now going to talk about one of the most important chemicals in the body. In fact, I would say that there are two chemical things, that are the foundation of life, and this is one of them, and that's water. All life on Earth, all life that we know of, most life that we can even conceive of, is based on water, liquid water. Liquid water is absolutely necessary for life. There's a reason why the term water of life exists. Water is ubiquitous to life. But why? Why is all life based on water? It has to do with one simple property of water that we've already talked about, and that is its ability to form hydrogen bonds. Water is a very polar molecule. It's H2O. We know this. It has an oxygen. That oxygen has two what are called lone pairs of electrons. Oxygen normally has oxygen normally has 6 electrons. It wants 8, so it shares with two others. It's going to share an electron with a hydrogen, and it's going to share an electron with another hydrogen. And it's 2, so it has 6, 1, 2, 3, 4, half one of these two is 5, one of these two is 6. Now it has 8, because it also has the one that it's sharing from each hydrogen. These ones that don't participate in a bond, those are called lone pairs of electrons. These, if you'll recall, are polar covalent bonds, meaning that they have a partially positive side and a partially negative side. That's due to the fact that the oxygen is more electronegative, more electrograbby than the hydrogen, so the electrons spend more time with it. And so it becomes partially negative. The hydrogen loses those electrons. It doesn't exactly lose the electrons, but it doesn't get them as much as it wants to, so it becomes partially positive. Water, because of this, can form 4 hydrogen bonds. 2 that it donates. So for instance here, this water here is donating a hydrogen bond to that water here. It's donating a hydrogen bond to that water there. And it can receive 2 hydrogen bonds. To be on the receiving end of the hydrogen bond, you basically have to have a lone pair of electrons. And water has 2 lone pairs of electrons. This lone pair here can receive a hydrogen bond from that water. And this lone pair here can receive a hydrogen bond from that water. So in liquid water, pretty much every water molecule is participating in 4 hydrogen bonds. And then each of these other water molecules here is going to have 4 hydrogen bonds, and each of those is going to have 4 hydrogen bonds, and so on and so forth. That's a lot of hydrogen bonds. And remember, hydrogen bonds are the strongest of the dipole interactions. They're the strongest of the what are called intermolecular interactions, interactions that are not like bonds that hold a compound together, but bonds that hold a substance together, that bind one molecule to another molecule. In your body, you have different compartments of water. Water makes up a pretty large part. Depending upon whether you're male or female, it's about 2/3 to 3/4 of your body mass. The water can be in 2 spaces, right? It's either inside of your cells or it's not inside of your cells. The water in your cells is approximately 2/3 of the water. So 2/3 of your body's water is intracellular, meaning it is inside the cells. You've got about 40 trillion cells. So it's a lot of cells. They all are mostly water. Extracellular water. you've got a lot of water outside of your cells. This water is mostly in two compartments. It's in the blood, or it's in the tissues. Water in the blood is mostly called plasma. Water in the tissues is called interstitial fluid. All right? So interstitial fluid is water that is in the tissues in between cells. And transcellular fluids is another basically term for the same thing. Plasma is the watery portion of blood. Lymph is plasma that has been strained out of the blood and is gathered in your lymphatic vessels. And we'll talk about this more in ANP2. But about 1/3 of your body's water is in this extracellular, non-cellular water. You're going to want to probably know those numbers. What does water do in the body? Why is it so important? There's a few reasons. The first is probably the most important, the biggest, and that is that it is a mixing medium. What does that mean? That means that because of water's ability to form hydrogen bonds, it can dissolve things. And you've probably done this. You've dissolved plenty of things in water. You know that sugar dissolves in water, salt dissolves in water, Kool-Aid dissolves in water, lots of things dissolve in water. Water is sometimes called the universal solvent. Some things don't dissolve in water, mostly oils, things that don't have polar bonds. But for the most part, anything that has polar bonds can probably dissolve in water. When you have something that is dissolved in water, there are a few different types of things that it could be. These are all different types of mixtures. Mixture is something in something else. In these cases, the something else is going to be water. Water is therefore what we call the solute, or water is the solvent. It is what is dissolved into. A solution. A solution is when something is completely dissolved in the water. It's dissolved to the point that you can't see it at all. It's completely dissolved. The water remains transparent, non-cloudy. Sometimes it might have a color to it. If the thing that you dissolved in was colored, like a food coloring or a dye or something like that, but the light does not scatter off of the particles. Generally speaking, it behaves as if it was part of the water. There's no scattering, no cloudiness. Generally small, very hydrophilic, that means very polar things, will form solutions. Think of salt water, sugar water, those are all solutions. You could form a colloid. A colloid is a mixture where the whatever is being mixed into the water is truly mixed. It's not a separate thing. It won't fall out. If you let it sit for a while, it won't all settle at the bottom. It truly remains suspended. But these are usually things that are bigger, and so they're not truly in solution, and they can scatter light, making a cloudy or opaquish mixture. Usually the things that form colloids are large molecules, often proteins. We'll talk about what exactly a protein is. But a good example of a colloid is milk. The protein in milk is mixed in. If you set a glass of milk out, at least before it, if it doesn't spoil, the white isn't going to settle out at the bottom of the cup. It will remain there in the water that forms up most of the milk. But you look at milk, it's opaque, you can't see through it very well. That's because it's a colloid. It's got big particles in it that are reflecting light. And then there is a suspension. A suspension is, well, here's a good example of a suspension. Take some sand, put it in water, shake it up a lot, right? You've got the sand, it's sitting there floating in the water. It's mixed with the water, but give it some time, it'll settle out at the bottom. That's what a suspension is. It is when you have large particles that are temporarily suspended in the water, but will settle out given time. This is often very large particles, not always as big as sand, but things like cells are often in suspension. Often if you let, for instance, say blood sit, or if you give it a little bit of a hand by spinning it in a centrifuge, the cells will settle out at the bottom because they're just suspended. They're not actually mixed or colloided. Now, those are solid things. It's also possible to have a suspension of non-miscible fluid. Most polar fluids, like, say, alcohol. Alcohol will mix with water. No problem. You pour them together, they mix. You've got a solution of alcohol and water. But take something like oil. Well, anyone who's ever had Italian dressing knows that water and oil don't mix. Vinegar is water-based, and oil is, of course, oil-based. And you get your vinaigrette dressing, and you've got a layer of water and a layer of oil. They don't mix. You don't want to pour that in your salad, so what do? You shake it up really, really hard. And what you get is what's called an emulsion. An emulsion is where you have very, very, very small particles, usually spheres, of some liquid, often an oil or hydrophobic substance, that is suspended in water. And so you will have little droplets of oil that are suspended in your watery vinegar medium, and then you pour that on your salad. But much like a suspension of sand, give it some time and it will settle out again. You'll get a separation of layers into oil and vinegar. Here you can see the dissolving property of water. One of the things that water is really good at dissolving is ions, right? So you take salt, right? So salt is sodium chloride. In salt, what you have is these negative chloride molecules and these positive sodium molecules. They've formed an ionic bond together and are currently in a crystal. But remember that this negative force, it goes in all directions. So it's attracting positive charges from all directions. And it doesn't care what's next to it, as long as what's next to it is positive. Similarly, these positives are attracting negatives in all directions. And it doesn't care what's next to it, as long as what's next to it is negative. Well, what about water? Remember, water, OH, has a partially positive end and a partially negative end. And so since this chloride here doesn't care what's next to it as long as what's next to it is positive, well, when it's in a salt crystal, like some table salt that you'll pour into some water or something like that, it's surrounded by these negative or positive sodiums. Well, let's see what's happening here. Remember all of these water molecules, this white end here is the positive hydrogen end, and all of the positive ends of these water molecules will surround the chloride. And the chloride then says, I don't need you anymore, sodium. I've got my water group around me, and they're all giving me their positive charges, so I can just go off on my own and just be free in solution, in water. And the sodium says, well, I don't care. I don't need you, because I can go off with this water, and they're all putting their negative ends to me. So we've got this chloride here, which is totally happy because it's surrounded by all of these partial positive charges. And we've got this sodium here, and it's super happy because it's surrounded by all of these negative charges right here. And so now the sodium and the chloride don't have to be in a crystal. They were only in the crystals because all of these negative charges we're attaching to positive charges, and vice versa. Put them in some water, and the water goes, dude, I'm negative and positive. I can go both ways. And the sodium and the chloride then can just, separate and hang out with all of these waters all the time. That's what happens when you dissolve salt in water. This is how water becomes a solution. What are the other functions of water in the body other than as a mixing medium, a solution forming medium? Well, there are some important ones. Transport. Water is the way things get around in your body. Specifically, blood is mostly the way things get around in your body, but blood is mostly water. All of the things like ions, electrolytes, sugar for nutrients, hormones, controlling signals, proteins, oxygen, all of those move around your body through the blood, and then they exit from the blood and flow through your interstitial fluids until they get to your cells. And then even in your cells, it's the fact that they can float in this watery medium called the cytoplasm inside of the cell that they can move places within the cell. So transport. Water is the way things get around inside of your body. A lubricant. Right? So your body moves. Well, the way your body moves is you have joints. Joints are, we'll talk about this more when we talk about bones, but basically anytime you have two bones getting together, you got a joint. Well, anyone who's ever worked on cars or bodies or anything else knows that when you've got two solid things that are trying to move against each other, it creates friction. Friction's bad. Friction causes damage. You don't want friction. So what do? Whenever we have two joints rubbing against each other, like let's say we have a bone coming down here, right? And then it's going to be articulating with this other bone right here. Where these two things rub up against each other, you will have a joint capsule, and that joint capsule is going to be filled with something called synovial fluid. And that synovial fluid is mostly water with some proteins in it. It's got about the consistency of egg yolk, and it acts much like the oil in the pistons of your car. It acts as a lubricant. It stops the bones from actually rubbing against each other and doing damage to each other. There are many places in your body where water or water in mixture acts as a lubricant. It surrounds your lungs so that when your lungs expand and contract when you're breathing, you don't have your lungs rubbing up against the tissue next to them. So that when your heart beats, it's in a fluids-filled sac, and so that when your heart expands and contracts, it doesn't rub up against other things. That's because it has this fluid cushion lubricating it. Thermoregulation. Water, one of the reasons why water is so totally awesome is because it has all of these hydrogen bonds in it. Well, breaking bonds takes energy. If you're going to take water that's in a liquid form and turn it into a gas, that's basically boiling it, you have to break all of those hydrogen bonds. And it could form up to 4 hydrogen bonds, and most of them are forming 4 hydrogen bonds. You have to break 4 hydrogen bonds. And they're strong hydrogen bonds for every 1 water molecule that you release as a gas. That takes a lot of energy. That means that you can put a lot of energy into water, and it doesn't change much in temperature. Take something metal. Don't do this, actually. In fact, explicitly do not do what I am about to tell you. But if you were to take something metal and you were to put it on your stove, it would heat up really, really fast, and you'd burn your hand. Take some water, put it on your stove, and it takes a while for it to heat up. That's because of these hydrogen bonds in the water that make it able to absorb a huge amount of heat when it evaporates, or before it evaporates. So that means that it can hold a lot of heat. The way your body moves heat around is through water, through blood. Blood circulates to the inner part of your body where it picks up heat, and then it carries that heat everywhere else where it radiates it out. When your body wants to cool down, your body will flush. More blood will be going to your skin where the blood will carry heat to your surface and it will radiate away from your body and you'll lose heat. When you're trying to conserve heat, maybe you're cold, you'll go pale. That's because your body is holding all of its blood inside and not letting much of it to the surface so that it doesn't lose as much heat. When you sweat, what's happening is that water is evaporating. Remember how I said that in order for water to become a gas, which is what evaporation is, you have to break those 4 hydrogen bonds, and that takes energy? Well, when your sweat evaporates, it takes energy for it to evaporate. That energy comes from your body heat. So in order for it to evaporate, it has to use your body heat to do that. That cools you down. That's evaporative cooling. It's the same principle that like a swamp cooler works on. That's how your body regulates, well, it's one of the ways that your body regulates its body heat, by using water to take heat away. Chemistry. Many chemical reactions in the body, in fact, pretty much all of the chemical reactions in the body are water-based. So they only happen in a liquid medium. If it weren't for the water, they wouldn't happen. Usually they're reacting with the water. We'll talk about hydrolysis and dehydration reactions. As you can tell from the hydro and those types of reactions names, they involve water. So water is absolutely necessary for most of the chemistry that happens inside of your body. And last, this is sort of general catch-all category, homeostasis. Your body maintains water homeostasis. This isn't so much a function of the water in your body as how your body regulates all of the other functions that water does, right? Your body needs water. If you don't get water, you die. And your body has to take in water, you drink, and your body has to get rid of water, you pee. And in theory, if you pee less, you would need to drink less. But part of the flow of water through your body and out of your body is that it's going to be carrying, again, this is transport, metabolic wastes, all sorts of bad junk that your body makes are going to be carried out when you pee from your body. And so you have to pee a certain amount, or else poisons will just build up in your body and you'll die. So the flow of water through your body and out again is necessary to maintaining homeostasis. It's going to carry away all of that, all of those toxins and poisons and all of those bad contaminants. Generally speaking, we have some terms for things based on their ability to mix with water. A hydrophilic thing. Hydro means water. Philo means to love. So if you're hydrophilic, you are water loving. This is going to be something that mixes easily with water. In general, things which have a lot of polar bonds. So for instance, sugar has a lot of polar bonds. It's got 6 hydrogen bond forming OH groups in it. And so it can form lots of hydrogen bonds. If you can form lots of hydrogen bonds, you're going to dissolve well in water. You're very polar. The more polar you are, the more easily you dissolve in water. Generally speaking, ions are going to be the most polar things. So most ions will dissolve very well in water. So ions or full charges are more hydrophilic. Hydrogen bond forming things are the next most hydrophilic. Polar non-hydrogen bond forming things are less hydrophilic than that. And if you are non-polar, then you are not hydrophilic at all. You would then be hydrophobic. Again, hydro meaning water, phobos meaning fear. These are water-fearing things. These do not form hydrogen bonds. They do not form many polar interactions, and they do not associate with water. This is your oil that doesn't mix. It's usually made predominantly of nonpolar covalent bonds. An amphipathic molecule or substance is something that has a hydrophilic portion and a hydrophobic portion. So, like, it might have a big group on the end with lots of, like, charges and, polar groups coming off of it. And then it might have a big section here that is all non-polar. So this here is polar up here and non-polar down there. So if it's got both polar and non-polar sections that are like separated from each other, it's amphipathic. It has some parts of it that are hydrophilic and some parts that are hydrophobic. These are going to be terms that are very useful to us when we discuss certain chemicals in the body. That's it for this lecture. Next, we will be talking about pH, which is another facet of water. In biology, it's mostly a property of water and how water interacts with other things.